For nearly a century, our model of the universe has relied on a single event, a rapid, outward expansion of all matter and energy beginning 13.8 billion years ago. Standard physics traces this expansion back to a singularity, a mathematical point where everything in existence is compressed to infinite density. In modern physics, infinity is an error. It indicates a flaw in the model rather than a physical reality. Einstein's general relativity cannot predict what happens at infinite density. At this scale, the equations failed to describe the behavior of space and time. These singularities indicate that our current description of the earliest moments of the universe is incomplete. A 2026 study from cosmologists in the UK and Barcelona proposes a model that avoids the singularity entirely. Their research suggests the Big Bang was actually a rebound, a transition from an earlier period of contraction into our current state of expansion. This model suggests our universe is a continuation of a prior one. This theory describes the end of a previous universe as a massive gravitational collapse, where ancient galaxies and matter were pulled inward. But instead of collapsing forever, this contraction reached a physical limit. The previous cosmos condensed into a nugget smaller than an atom, a finite, ultra-dense core that preserved its physical properties without breaking the laws of physics. By reaching a finite density rather than an infinite one, the math allows for a smooth transition from a collapsing universe to an expanding one. To understand what survived that transition, researchers calculated the structural limits of matter under this extreme pressure. They call it the 90-meter fossil limit. Their calculations show that at the peak of the squeeze, any compact object larger than roughly 90 meters across could withstand the pressure of the collapse. These survivors were black holes, remnants from the previous era that were too massive to be destroyed by the compression. This reversal is the bounce, the moment the extreme inward pressure flipped into the rapid expansion we observe today. While stars and gas were pulverized and recycled, these 90-meter black holes passed through the transition entirely intact. The presence of these black holes means the Big Bang was a transition between two cosmic epochs, rather than a definitive beginning. This heat map shows the faint radiation left over from the early universe. These fluctuations indicate that our cosmos still bears the structural marks of its previous life. Because these relic black holes already existed immediately after the bounce, the early universe did not have to build matter from a uniform state. This image captures the resulting spiral and elliptical galaxies. These ancient black holes acted as gravitational seeds, pulling gas together to form the very first galactic clusters. The arrangement of the galaxies we see today was determined by the gravity of those black holes left over from the earlier era. This leads to a possible solution for dark matter, the invisible mass that outweighs ordinary matter by 5 to 1. This visualization shows how a galaxy is held together. Physicists suggest that a significant portion of dark matter could be these relic black holes, surviving from before the bounce. If these invisible anchors date back to a previous universe, our history is much longer than 13.8 billion years. The Big Bang was a bridge between two distinct cosmic eras. Our universe began as a sequel, a rebound from a previous, dying cosmos. While that collapse destroyed almost everything, massive black holes over 90 meters wide were sturdy enough to survive the transition into our current reality. This provides a potential answer to the most glaring error in our map of the cosmos. When we weigh the universe, we find that 85% of its mass is completely invisible. Scientists refer to this hidden bulk as dark matter. We can detect its invisible gravitational force holding our galaxies together, but its physical identity remains a total mystery. It is impossible to grasp a fundamental structure of the universe when its primary ingredient is missing. A second problem has recently emerged from the deep space observations of the James Webb Space Telescope. High-resolution infrared scans have revealed these little red dots. They are massive galaxies existing at the very beginning of the cosmic timeline, far earlier than our current models allow. Standard physics suggests the early universe should have started as a smooth, featureless soup. These giants are too heavy and too complex to have formed so quickly from nothing. The missing mass of today and these early giants from the past share a single underlying cause. The latest research from the University of Portsmouth and the Institute of Space Sciences points to those surviving bounce relics as the common thread. A vast population of these relic black holes would create an enormous gravitational footprint, physically accounting for the invisible mass we call dark matter. This also changes the timeline for the first galaxies. Instead of starting from a blank slate, the early universe had a head start. Massive gravitational anchors were already in place the moment the expansion began. This animation shows that process in action. Because gravity was already concentrated in these ancient spots, primordial matter didn't spread out evenly. It was snared into the dense, pronounced clumps required to build a massive galaxy in record time. The first structures in our cosmos grew from seeds left behind by the previous one. In the early universe, vast molecular nurseries formed rapidly, with new galaxies swirling tightly around these perfectly black, ancient spheres. These black holes were linked across the void, forming an invisible, web-like structure that spanned the young cosmos. This scaffolding functioned as a high-tension magnetic network, dictating where and how matter could settle. This network aggressively pulled in thick clouds of hydrogen, crushing the gas together until it ignited into the very first stars. These fossils were the active architects that constructed our reality. Proving this requires scientists to find physical evidence of a universe that existed before our own. They are looking for those answers in the cosmic microwave background, the faint afterglow left over from the first moments of expansion. This map shows the earliest temperature fluctuations in the cosmos. Astronomers are now scanning these patterns for subtle gravitational echoes, specific signatures that would preserve the memory of the previous cosmic phase. Isolating these specific patterns would provide the physical fingerprints necessary to prove the universe was born from a bounce. If this theory holds, dark matter is not some exotic, undiscovered particle. It is the graveyard of a previous cosmos, serving as the invisible skeleton of our own. Every galaxy we observe today, including the Milky Way, was built upon the bones of a dead universe.